Welcome to the Office of Hydraulic Engineering Scour calculation example using the FHWA hydraulic toolbox. Today we will be going over an example problem to help you figure out what you need to do to get the results that we're looking for as outlined in the Location and Design Manual, Volume 2. And if you look in the Location and Design Manual, you will see in section 1008.10 Foundations, it describes what we are looking for in the sections shown here. Also, you can reference the Geotechnical Design Manual in the 1302 section on Scour, and that tells you the soil properties you will be looking for. And they also discuss culvert scour, which we will not be discussing today. So if you look at the 1008.10.1 section, it will direct you to use the FHWA hydraulic toolbox to calculate the scour. So all of the scour calculations in that software are based off of those shown in the Hydraulic Engineering Circular 18, otherwise known as HEC 18. And you can get this download free from FHWA at the link shown, or you can just type in FHWA hydraulic toolbox in your favorite browser and it'll be the first hit. And you can get that. It is free and it is not a large program, and you can download it and it will be ready to go. So let's start with our example. So today we're going to look at a three-span bridge because it has the three scour components that we want to look into. We have contraction scour, pier scour, and abutment scour. We see a bridge site plan, and we can see this three-span configuration. And I want to point out, circled on the top, we have the borings, soil borings for this project. If you don't have soil borings, you can't do a scour calculation, and you also need the hydraulic analysis as well. But you want to familiarize yourself with each boring and where it is, because you want to take the soil properties from a specific boring location depending on what you're looking at. So before we can perform the analysis, we need the soil properties. And if you look at the GDM section 1302, they'll show you an example of some scour data that we need. And if you look at their table, you can see it says what boring it is, and then the sample, and then the elevation, which is important, and we'll look at that later. And then we have the D50, and also has the critical shear and other columns that we have X'd out here in red. And those columns are not used in our scour calculations anymore. They're more of an internal thing for the geotech people. And the critical shear can only be used in scour calculations if it's derived through laboratory testing. There's also an equation you can use, but we will only use laboratory tested results in our scour calculations. So we also need hydraulic input. So a 1D HEC-RAS analysis gives us what we need. And you can see here, this is a cross-section output. If you're familiar with HEC-RAS, you're familiar with this. And we will be using HEC-RAS 1D for this example. There is also 2D analysis you can use, and specifically the SMS SRH2D data, it can be imported directly into the toolbox. So that's a nice feature if you can do that. And just to show you what can happen with the 2D, you can define arcs upstream and at the contraction section. and it will extract all of the hydraulic information, and it can adjust for skews. But what's really nice is that you can put all those values automatically into an input table, and so you don't have to pick the information, as we'll be showing in the next few slides. But that's coming in the future. So as we delve more into 2D analysis, we'll be able to use this more. But today we're doing the 1D. So let's start with that analysis. Okay, so to create a new Scour analysis, you open up the toolbox, and there is an icon which I have circled here that you can press, or if you can't identify through the icons, I'm not exactly sure what that's a picture of, but you can go to the Calculators tab and choose New Bridge Scour Analysis. So you can create a single analysis that will include all of the types you're doing, or you can create individual ones. It's up to you. So usually you want to start off with contraction scour first. That's the first scour that they talk about in HEC 18. So that's what we're going to do today. So when you open up the toolbox and then you started your project, you open up this interface, and you can see that it shows different types of scour, and you can see the contraction scour, and we check mark that. Although you see the pier and abutment scour, we're going to concentrate on the scour, the contraction scour in this particular section. So like I said, we need soil information. So we're looking here, and we have D50 that we're looking at. And so the critical shear properties have not been provided. And when you have a D50 that is below 0.2 millimeters, we're going to round everything to 0.2 millimeters because the toolbox can only work with 0.2 millimeter or larger for granular calculations. Also, we need the hydraulic data, and here are those cross-section outputs that we had seen earlier, and I have highlighted the specific ones that we're looking for. So you need an upstream section that is outside the contraction reach, and then one at the contracted section. So like I said, with the D50s below 0.2, we rounded it to 0.2. And a layer by layer analysis won't be necessary. And we inputted all of our hydraulic information that it asked for, including average depth and velocities and flows. And we came up with a contraction scour of 3.37 feet. So per L&D 1008.10.4, if the critical shear stress is from laboratories testing, then we can use that. So in this particular case, we're going to say that this information is from those tests. So with that, we can do different calculations using the cohesive properties. So for the computation method, you can see cohesive soil is what we picked. And then we add the hydraulic information, and you can see that the upstream depth and velocities and the other information there is the critical shear stress from the soil. And then we do the calculation, we can see we have 2.71 feet of scour, which is less than the 3.37. So now we're going to look at pure scour. So here's that interface again, and we've check marked the pure scour. And then we hit the define button, and we have to fill that in with information. We can look here. Here's soil information again. And here is the hydraulic information. So we take those two and we choose the HEC 18 method, which is the only method we're allowing right now when you don't have the cohesive properties. And you can see we added the hydraulic information there of the upstream depth of water and the velocity upstream, and we came up with the scour depth. And if you'll notice, the HEC 18 method does not use soil properties. It is dependent on the velocities, and the angle of attack can do a lot to it also, and the configuration. So we see here we came up with 5.38 feet of pure scour in this situation. So again, if we have the information for the cohesive soils, and in this case the erosion rate, which is calculated from the critical shear found in the tests, we can then use the cohesive method to calculate pure scour. So you can see we've chosen the cohesive materials computation method, and we fill in the information from the hydraulic section and then from the soil section, where you can see we've got the erosion rate, initial erosion rate. And then we come up with the depth, and the depth is 6.19 feet in this case, because if you look back at the soil properties, the first half a foot was granular, and we're going to assume that that scours completely because of the previous calculations, and then the further scour will occur in the cohesive material as shown in this calculation. Now we're going to do abutment scour. So a hard part to figure out sometimes, where is the abutment scour happening? And on a spill through type abutment, it's happening at the toe of slope where the embankment intersects with the floodplain, as we can see in the image on the left. And then the image on the right kind of shows you where that would happen and what would happen. So we'll see more specifically where that would be in this slide. So if you look around, where would that be? So you look at the plan view and you see where the elevation is the same on both sides. So we're trying to define where the embankment is again on top of the existing floodplain. And the cross section, that's real helpful too. On the right, it shows it's about 859.5, which coincides with the number we're seeing on the left side in the plan view, which is 860. So we're going to use that when we're looking at the soil properties. So we know that we want to look at the properties starting at around 860. So here's that interface again, and we choose abutment, left and right. We're only going to do one in this example, but remember there are two borings, one for the left abutment and one for the right abutment, and use the correct soil properties for that particular abutment that you're looking at. So we're also looking at the hydraulic information. So we've got flow and the top width in the main channel section, and the flow and the top width at the contraction section. And one thing for the abutment scour, which we will be using the NCHRP method, you don't use the total flow, you use the flow per lineal foot. So in this case, for the main channel, we take the 884 and divide it by the 57, and we get a 15.44 flow per foot, and then do the same type of calculation for the constricted area. So this is a little different than the contraction scour. And here again, we're looking at the soil properties. So we know the toe of slope is at 859.9. So we look in the table here and we can see where the elevations are. So we're taking the information from approximately where this begins. And in this case, they're all below 0.2 millimeters. So we're going to round it to 0.2 anyway. So we see the computation method is NCHRP, and we have the unit discharge that we calculated in the previous slides and put that into here, and there's the D50 of 0.2, and then we pulled the upstream flow depth and the flow depth at the prior to scour from the cross sections, and we came up with 6.38 feet. Now, abutment scour is not in addition to the contraction scour. It includes the contraction scour or is addition to it. So the total scour at the abutments is 6.38, which is more than what we calculated for the contraction scour, which makes sense. So here's our total scour. So without the cohesive soil properties, we can see that the contraction scour is greater than with cohesive soil properties, which is usually always the case, and it's more visible to see the differences with greater flow. So this particular bridge did not have the greatest amount of flows, but it's very typical for what we're seeing here in Ohio. And then the local pier scour was actually less without the cohesive properties, and that's because it doesn't use soil properties. And then the local abutment scour is the same because of the actual properties that it does use. So when we look at the total scour, and we're just going to look at the without cohesive soil properties, so we have the contraction scour, and then the pier scour does include the contraction scour. So you include that. You add the 3.37 to the 5.38, and we have 8.75 at the piers. And then we have abutment scour is a 6.38, and that scour starts at the toe of slope, so that elevation that we called the toe of slope. Now, those are the scour depths. We want, and the bridge people and the foundation people want a scour elevation. So you should take that depth and apply it and provide an elevation so that the foundation people know how far down and at what elevation the scour does occur. And if you look in our location and design manual, volume 2 at figure 1008-19, you can see a scour plot example and a lateral stability example. So if you have a channel that is meandering, you need to do the pier analysis as if it was on the main channel, because the channel may be at the pier at the time. And if it drifts towards the abutments, you can use that elevation as well. And we also want a scour plot that shows the scour at each location. And this figure helps you determine where you should show that elevation. I can't take any questions on this video presentation, but if you do have questions, please call our office and we'll be happy to answer them. Thank you for watching this presentation.